We are looking at the turning gamma subunit and the epsilon subunits, and there's the C ring in the membrane. The F1 complex is outside of the membrane, while the F0 complex is embedded in the membrane. There's the stalk, including the delta and the B subunit. The alpha subunits are shown in light pink. The beta subunits are magenta. In the middle, the central stalk is rotating. The B subunit stabilizes the hexamer, which means that the hexamer can't rotate. We will now look at a rendering of known structural states and the conformational changes that are happening. The beta subunits are seen as a ribbon diagram. The ADP and inorganic phosphate diffuse into the active site, and the ATP has just been released, and simultaneously the conformational change occurs in the beta subunit. If we zoom into the active site, we can see the molecular structure of the substrates and the chemical reaction. Here is ADP with its two phosphates. They are all held in place by a network of hydrogen bonds mediated by the amino acids in the folded structure of the beta subunit. Hydrogen bonds stabilize the base and the sugar, but really primarily the base. There's also a magnesium ion that plays a critical role in not just stabilizing, but also neutralizing the charge of the phosphates. Notice the conformational changes that are happening when the inorganic phosphate comes in. There is the promotion of a planar transition state. Synthesis of a new phosphodiester bond is catalyzed, and then the subunit switches to the open conformation. Upon this reconfiguration in the beta subunit, ATP is ejected from the active site. The enzyme then resets and restarts the synthesis of another ATP molecule. This is a summary of the events at the active site. It is also intriguing just how the C ring rotates. We can start with the analogy of a water wheel. We can easily grasp the idea of how a water wheel rotates. It's driven by the flow of water, allowing the wooden fins to go in a particular direction. Thus, the rotation happens in a specific direction. If the water was to flow in the opposite direction, you would see rotation of the water wheel in the opposite direction. Here we see the C ring and the A subunit. We don't know the full structure of the A subunit, but we know that there's an access channel for protons on the A subunit right in the intermembrane space. And there's a separate egress channel for protons on the matrix side. In this animation, you see protons flowing out from an interface between the C ring and the A subunit. But what drives the specific direction of this rotation? For example, if we were looking down, it is always a counterclockwise rotation. Why and what drives that? On each of the C subunits within the C ring, there is a proton binding site. Notice the high concentration of protons on the intermembrane side and their flow to the lower concentration on the matrix side. Protons load from the highly concentrated intermembrane side onto the C subunits, and they are released on the matrix side where the concentration of the protons is low. But why can't protons go around the other way as well? In principle, just as in the water wheel analogy, the C ring should be able to rotate in either direction, shouldn't it? There are two interconnected reasons for this unidirectional movement. The amino acid side chains in C subunits would repel the bound proton, so that when a proton loads from the intermembrane side, the C ring cannot rotate back in the opposite direction because it is energetically unfavorable. Rotating counterclockwise, on the other hand, is energetically favorable because there are no repulsive interactions. Remember, there's a concentration gradient that favors binding of protons on the intermembrane side and the release of protons on the matrix side. So in summary, the proton gradient determines the direction of the rotation, favoring movement in the counterclockwise direction of the C ring. This avoids unfavorable interactions with the amino acid side chains of the C ring.